For any theory, why this theory?
You can't simply say, well, we want a pure Big Bang.
If you look at the history of mathematics, where these ideas about mathematical structures come from, they often come from two sources, from physics and the physical world, and then from number theory.
And it turned out that the guys doing not good science ended up doing great science. And I think that that's where we are now.
The key justification for using a theory for the evolution of the universe is that it has to be simple. It has to be a simple explanation for the observations that we have today. So what physicists have done to replace this problem with the singularity of the Big Bang is that they have replaced part of this evolution law early in the universe. So you take the normal Big Bang theory up to a certain moment in time, depends on exactly how you want to do it, then you add a different evolution law and you use this evolution law to go back further in time. This gives you a different initial state and it can get rid of the singularity and it can have all kinds of other consequences. So you change the equations and then, as I said, you'd always get an initial state that then fits together with those equations to give you what we actually observe. And there are lots of different theories that have come out of this. For example, there may not have been a Big Bang, there might have been a big bounce. So there was an earlier universe which contracted and then it didn't go to a singularity, but it just shrunk to a very small size and then it began to expand again. There could be cycles. Roger Penrose, for example, has a model for a cyclic cosmology. There's an idea that's called asymptotic silence, where basically the early universe was just sitting there for a really, really long time not doing anything, and then suddenly it decided it'd expand. This also gets rid of the singularity. There's the no boundary proposal from Hartley and Hawking, where you basically get rid of time entirely, so there's only space, 4 dimensions of space. Some think maybe there was neither space nor time, there was just a pre-geometric phase, maybe some kind of a big network that had to condense into a form where it would give rise to something that approximates space-time to a very good precision, 5-dimensional black holes, string gases, and so on and so forth. It's a really long list. But those ideas all work the same way. You change the evolution law somewhere back in time, and then you have a different initial state. Now, what's the problem with this? Well, as I said, a good scientific explanation must be simpler than the observation it's trying to explain. And the problem with all those theories for the early universe is that they make a simple story more difficult. But a good scientific explanation should be as simple as possible, and you shouldn't add any unnecessary assumptions, no matter how much you would like there to be a cyclic universe. It's as Laplace put it, I had no use for this hypothesis. We also don't really have a use for the hypothesis of an infinite number of cycles. It's absolutely unnecessary to explain what we currently observe. And so this is why I say all those stories, they're basically tales, they're creation myths written in the language of mathematics. They're mostly not wrong in the sense that all those physicists, I mean, it's not like they're dumb, right? They make a big effort to get a theory that actually agrees with observations. Of course, I mean, there are some people who argue that this or that idea doesn't actually fit with observations, but that's a little bit beside the point. Mostly they're trying to actually get the observations out right. So they're not wrong, but we can't tell that they're right because they just add this unnecessary structure at a time where we don't actually have any data.
But I want to get back to the basic theme, which is is the standard model, the Big Bang, in trouble? The contrast is basically between a theory that requires imaginary entities that are made up after the fact, which my colleagues seem to express a good deal of skepticism about. You can't simply say, well, we want a pure Big Bang without inflation, without dark energy, without dark matter, because the theory collapses. These were introduced to overcome severe conflicts with observation. If you don't have inflation, then the theory predicts a microwave background that would be completely crazy quilt. It wouldn't be at all even. If you don't have dark energy, you have a problem that the universe is younger than the Milky Way galaxy. If you don't have dark matter, the universe can't form any clusters or galaxies at all. It doesn't form structure. So you can't simply say, well, we want the pure one without all this fairy dust. In contrast, what we are talking about is an alternative that relies on verified laboratory evidence. And conversely, theories that are developed for astrophysics can be applied here on Earth. And I want to again come back to our own work as an example. 40 years ago, I developed a model of quasars based on phenomena that observed in a device called the dense plasma focus, which spontaneously forms, without gravitation, extremely dense plasmoids, very energy concentrated blobs of plasma that emit beams of energy, just like a quasar. I developed this model quantitatively, applied it to quasar data, and then used it to design a version of our device. With that device, we achieved 7 years ago record confined temperatures that have never been achieved in any fusion experiment, temperatures of 2 billion degrees, which is about 200 times the temperature at the center of the sun. This is the sort of confirmation of lab-tested results that we have to use to explain the universe. If we go and say it's okay that we have all these challenges or tensions, that our plane has crashed so many times, as long as we can introduce dark matter, dark energy, or my favorite, cannibal dark matter, which has been proposed to resolve some of these questions, that's not doing science. That's ex post facto explanation, sort of just so stories.
So by material, I think of objects in space and time. And physicists such as David Gross and Nima Arkani-Hamed are now telling us that space-time is doomed. By that, they mean space-time is not fundamental. And they're not just throwing up their hands and giving up. The physicists have now found structures beyond space-time, like the positive Grassmannian, the amplitude-hedron. And so this is all new. That's only been in the last 10 years that they've, for example, had the amplitude-hedron. But the idea that space and time and objects like bosons, leptons, and quarks, particles, and so forth, are fundamental is now no longer the received opinion. There's something deeper, like the amplitude-hedron, and beyond that, something called decorated permutations. And so the idea of reductionism is also doomed, according to physicists like Nima Arkani-Hamed. The idea that as we go to smaller and smaller scales in space and time, we find more and more fundamental laws and more fundamental entities, that's also dead. So I'm not a panpsychist in the sense that I don't want to try to put consciousness in the elementary particles, because the physicists themselves tell us that space-time and the so-called elementary particles are doomed. We have to go entirely outside of space-time and trying to put consciousness inside of particles or behind particles. We have to have a much deeper framework. Now, evolution by natural selection also agrees. This is work that I've done with some of my colleagues. It also agrees that our perceptions of space and time are not an insight into the nature of reality. They're merely an interface, an artifact of our perceptual sensory systems. there's a technical question. What is the probability that evolution would shape sensory systems to see any aspect of the structure of reality as it is? And it turns out the probability is precisely zero that any sensory system has ever been shaped to see any aspect of the structure of objective reality. So evolution and the physicists agree. Space-time is doomed and reductionism is doomed. And so we have to look for a theory of consciousness outside of it. And I would agree with Sam that solipsism is not the answer either. We needed a theory of consciousness that's not solipsistic.
I think the observations and the critique that I can come forth with is historically based, it's philosophically based, and it's trying to take an outside observer look in terms of plausibility of how well do we actually know how all these things stack together. But it's not my role to judge the merit of a scientific theory. That is for the scientific community. That is one consequence of physics and philosophy sort of breaking apart. So right now we have cosmologists or scientists, more generally speaking, are setting all the terms for how to approach and understand the universe. And they're also the ones who judge whether they think a theory has more merit or not. To some degree, the core of the model is taken as a matter of faith. And that if you are to question it, then you risk running afoul of a lot of things regarding, funding and career and so on. On the one hand, especially if you are a scientist, you can build a career now on challenging some of the upper blocks, so to speak. For example, dark matter. There is a real challenger to this particular part. But I find very few scientists are willing to look at the more questionable assumptions underneath the core building blocks of how we got here in the first place. And the reason why it strikes me is not because those blocks are so solid and proven beyond doubt when you look at them closely. It's more that if you are to put them into doubt, or if they are slightly wrong, or if you are to remove them, then you lose the guiding structure you have to make sense of the universe. It's like taking a framework away from a scientist is the same as making them blind. Like, then we have nothing to guide us by. So I think that there is a tendency to want to cling on to the basics because it becomes very difficult to do scientific research. It is much more convenient to add things to the model and preserve the existing structure than it is to radically rethink it. It's one of the legacies of the split between philosophy and science in the 20th century is a strand of thought sometimes called logical empiricism or positivism, which really greatly influenced science into this rise of the professional school of science, is to believe that science has to be free of metaphysics, and that it's the ideal is to have a science that's pure without having to make any such grounding claims or any such framing devices. So in my view, this is a delusion, and it would be much better if we could speak openly about what the guiding assumptions or the premises for a theory are, and speaking about them openly instead of trying to hide them away. If you look at scientific texts or any scientific calculation, if you look at Einstein's own work on general relativity, he has a couple of pages describing the assumptions or the principles that he uses, and then there's pages of mathematical equations. Now, most physicists would be trained to look at his math and then to train to look at the field equations and to kind of gloss over the assumptions part. But all of those assumptions are themselves up for debate or questionable. They're ways of framing the problem. And I don't think you can ever get around that.
In the sort of mid 20th century, Feynman, Schwinger, Tominaga, Dyson, and most particularly a guy named Ken Wilson came up with a program called renormalization theory. Renormalization theory effectively taught us, if you have a flawed theory, how to make sure that the flaws don't infect all of your answers. So as long as you have a flawed theory, make sure that you have like a flaw in the numerator and the exact same flaw in the denominator. And whatever that flaw is, you may not be able to discern it, but at least you can cancel it, right? So it's similar, for example, to Black-Scholes pricing, where you have a security and you have an option on the security. Whatever the uncertainty is, it's the same uncertainty in both. And so you should be able to hold one long, one short, and you end up with a risk-free bond whose price doesn't vibrate. This trick, in some sense, humbled the physicists, and they started to realize that all of their theories were sort of trapped within an energy regime. And they were afraid to guess outside of their energy regime because Wilson taught them what could be lurking. But my belief is that that's the wrong lesson. If you ever watch like Wheel of Fortune, they spin the wheel and they have to guess like a phrase, and you see a very long phrase, and somebody says, is there a P? And there is a P. And says, can I guess? You're like, well, you only have one letter. It says, look before you leap. Oh my God, that's true. We've got to guess. And the physicists learned the wrong lesson, in my opinion, which is it's not enough to determine the answer. But that doesn't mean you can't guess, and it doesn't mean you shouldn't guess. And I actually think the dear Lord that you and I don't believe in has left a large number of clues that are sort of subtle, right? Because like in that situation, it's the letter pattern that really determines that those anomalous guesses and their likelihood of being right. We can use far less information than you would imagine to actually guess if the theory has order. And this was, of course, the problem with the double helix. Why Rosalind Franklin didn't get it is that she was being a good scientist. And she was saying, we don't have enough information to guess it's a helix. And Jim Watson and Francis Crick were not good scientists. They were great scientists who weren't very good. And the difference between good and great is that great honestly realizes that you have to break the simplistic rules of science to make an advance sometimes. So they said, let's only search for helices. And she thought, well, you guys are just mimicking Linus Pauling because you're wannabes, you're thirsty, and you're trying to get something like the alpha helix in protein. And it turned out that the guys doing not good science ended up doing great science. And I think that that's where we are now.
When I was a student in Chicago doing research, I did have this amazing dream where I had this vision of this equation. And then when I woke up, I kept thinking, what was it? And of course, since then, I'm a teacher. I teach in a state school. My feeling that I'm glad, actually, because from the perspective of students, it seems very arrogant and sort of superior to think that you could encompass all of this amazing world. And then, leaves have been embracing quantum mechanics long before we found out anything about it, to photosynthesize, haven't they? So, and students, my passion is about enabling them to do amazing stuff, and they can. And yet with this it sort of permeates across education. We have a very boring way of making sure that they don't really get excited by the awe and wonder of physics. We teach them very boring models of the solar system to model the atom, when actually they should be realizing that there's no such thing as position and sort of an essence of quantum mechanics. I'll do a quick poll. Who loved physics at school? Oh, well, perhaps I'm completely wrong then. So I perhaps have a biased audience. Just a bit of... But, if we are set in thinking there are set ways, then there's huge limits on particularly young people to think that there are avenues open for them. For example, only 10% of string theorists are women. And we know what the trouble is about the lack of women in physics. Also other sorts of modes of thought. Why is it that we've got 10,000 times the amount of energy that we need arriving every day from the sun, and yet we sort of are trapped in ways of thinking? I was reading about indigenous science. We wiped that out and lost some of the amazing understanding of how they built the pyramids and everything. Science has amazing successes, and of course I love it, and I think it's amazing and can improve the world. But I think we should be having different views and the opportunities, especially for young people, to see that there are different ways of thinking, and that you don't have to be a certain way to go down, say, string theory and totally mad mathematical physics, which nobody can understand. And so I feel that I'm quite glad that perhaps this sort of constraining idea is waning.
I think the point of view people often start with is that the classical reality that we're used to when we're seeing everything around us and this picture of the space with the stuff in it moving around that we're used to, that's easy to understand. The hard thing to understand is what's happening at this microscopic level. And I actually like to turn that around. I think especially when you're looking at the mathematics of it, the easy thing to understand is the quantum level. I mean, I could write down Schrödinger's equation. I could tell you very, very precisely exactly what is going on, with a few particles behaving in a quantum mechanical level. How, once you put 10 to the 23 or whatever these particles together, and with very complicated physics, how the classical world and what we see and what we think we understand every day, how that emerges from the quantum system.
That's the tricky part.
That's really, really hard to understand, and it's actually behind our this kind of question about, how do you interpret quantum mechanics? What is a measurement? All of those questions are actually very, very difficult physical questions because of this problem. I think I sometimes say that I take kind of a radical Platonistic attitude that not only does math exist, but it really actually is the same thing at a fundamental level as physics. And some of the reasons for saying that are actually just the experience, especially in recent years. If you look at the history of mathematics, where these ideas about mathematical structures come from, they often come from two sources, from physics and the physical world, and then from number theory. And traditionally, these are two completely different things. That the arguments about despite the example you gave, even arguments about prime numbers and the structure of numbers, and arguments about physical reality are just completely different parts of the subject. But in recent years, there have been ways in which you can see these things coming together, and some of the most exciting research is happening now in mathematics. At the frontiers of mathematics involves ideas which, where there's a clear component of this. I mean, just to give a name to it, there's this idea of the geometric Lagrange program, and that is something that kind of came out of number theory, but it brought connections to physics and to geometry, and it's, when you're looking at the deepest level, just these connections between what you thought was purely mathematical objects and what you thought was physics are just striking relations, and we're learning striking things about that.
I mean, so string theory actually, it's not a child. It's 50 years old.
Okay.
So actually, over
as
50,
theories go,
55 actually. So I think some people in, say, the late 80s, which is long before I became involved in this field, they did overhype things, right? They said, well, this is going to solve everything. And I have to say, maybe it's them, but maybe it's also the media. They like this, right?
Well, the media is guilty of everything,
clickbait
yes.
of this. And so, of course, there's an overpromising.
Yeah.
And, a lot of the people in the field were I'm told, and they tell me, were very, very uncomfortable about that. Instead of saying, we have a theory that might answer some aspects of the ultimate theory of everything, isn't that cool on its own? Saying, wow, we're going to answer the theory of everything and we're going to have a description of everything in the next 10 or 20 years, which was just promising far too much and was not going to not going to meet people's expectations. So, I actually don't disagree with Peter, in fact, about, current versions of quantum gravity theories are very, very poor at describing cosmological physics, so things which are changing over cosmological timescales. And so we're always extrapolating from our understanding of in different regimes. And so we're being told that actually our extrapolation must be wrong. But I take that as actually interesting because it's saying, well, actually, we've got to think about other things we can do. So I've diverted a bit away from your question, but I think, in the media, there's been almost this overhyping. I think in the actual scientific community, it's a much more measured approach of actually it's one step forward at a time, one bit at a time, and there is progress, and it's important not to sort of overpromise what you do.
What I showed was that singularities, you used the word singularities, we'll come to that. Singularities are a robust prediction of general relativity. Now you see, the picture we have of a black hole is you've got a certain region where things can't get out of. It's called the horizon. So if you fall through Imagine a big sphere, that if you fall through that sphere, there's a point of no return and you can't ever get back again. And that's the horizon. Now the singularities are right in the middle. And the black hole is basically why you can't see the singularities. I mean, what I showed, let me backtrack a little bit. I get my dates probably wrong when I say this, but in 1939, there was a paper written by Oppenheimer of atomic bomb distinction and all that stuff. Oppenheimer and Snyder, who was a graduate student, I think, of his, and they studied what's called a dust cloud. Now, dust means the material has no pressure. And it was a completely spherically symmetrical, you have this dust collapsing inwards. Now, the thing is that, first of all, it has no pressure. Secondly, it's focused exactly at that central point. So the fact that it falls in, there's nothing to stop it. And the density is likely to get bigger and bigger and bigger and become infinite. And this was the picture that Oppenheimer and Snyder produced at that time. Now, is that realistic? Well, people said, well, first of all, material has pressure. So more importantly, if you have exact symmetry, then of course it's got nowhere else to go apart from right to the center. So the fact that you get singularities is not perhaps a surprise.
I think science and religion aren't at war. There are a lot of people who try to play those two out against each other, but if you look at what's actually going on in the foundations of physics, then many of the ideas that physicists consider there, especially about the question how the universe began, they're basically extensions of some of those originally religious or spiritual ideas. They're just formulated in the form of mathematics. And there are many of those religious ideas which are still compatible with all we currently know. There are also some things that may forever remain unknown. I already said, I believe that ultimately we probably won't be able to figure out how the universe began, because it seems to me that this is just a way that science is fundamentally limited, that we aren't allowed to make a story more complicated. Though that may not be wrong. Like there may have been a more complicated universe before ours. It's just that the way that science works, we would never be able to say whether it was actually correct. Another question to which we may never find an answer is if there's actually a theory of everything. So this isn't something which I talked about here in any length. Again, that's something that I talk about in my book. But to make a long story short, the problem is there will always remain the question for any theory, why this theory? We know that the universe has to be in some particular way. I mean, we know that it is some particular way and not any other. So we need a theory that agrees with what we observe. But then there will always be questions in this theory which we can only answer by saying, because it describes what we observe. So I think this is another way that science is fundamentally limited.